Stand closely near the heavy concrete of a modern runway and watch one of the largest commercial machines ever engineered spooling up for takeoff. The massive fan blades spinning rapidly at the front of a jet airliner do not merely push the aircraft forward. They actively pull the surrounding environment directly inside. On a perfectly clear afternoon, this looks like an entirely flawless process of modern engineering. But the atmosphere is rarely entirely empty. When the sky shifts, dragging a faint, bruised orange tint across the horizon, it is carrying billions of suspended mineral particles, crushed quartz, and jagged silicate sand. An accelerating jet engine acts as a colossal vacuum. It cannot separate the pristine machine from the harsh desert. It must ingest the desert to survive. We often assume that major infrastructure failures announce themselves with a sudden, catastrophic event, a loud noise, a dramatic shutdown, a flashing headline. But in an environment this extreme, mechanical degradation does not have to begin with a sudden bang. It can easily begin with a million microscopic, invisible impacts. A severe, blinding dust storm might conclude after just a few hours. The skies clear up, the ground crews return, and the flights resume. But the physical traces left deep inside the intricate propulsion systems remain. What if the very air sustaining Dubai's aviation empire is also slowly wearing it down? To fully grasp why a microscopic grain of suspended dust matters, we must first measure the sheer scale of the system pulling it in. Dubai has engineered a geographic crossroads that defies the natural limits of its landscape. In the year 2025, Dubai International processed an astonishing 95.2 million passengers. The tarmac recorded roughly 454,800 flight movements. This is a relentless, synchronized machine operating at a staggering global scale. And it has to operate relentlessly. This aviation network is not just a transit hub. It is the absolute lifeline for modern economics and the construction miracles that define the city. Dubai's highly leveraged luxury real estate, its sprawling high-end hospitality sectors, and those exclusive, Michelin-starred restaurants sitting high above the Marina are entirely dependent on a permanent, uninterrupted influx of arrivals. We have seen the fragility of the Dubai tourism market when external crises hit. Without planes landing constantly, those immaculate luxury spaces sit dangerously empty. The hospitality economy cannot tolerate a severed supply chain. Yet, every single one of those 454,800 takeoffs and landings forces a highly sensitive jet engine to breathe the local atmosphere. As the frequency of flights increases to feed the expanding tourism sector, the total number of times these engines are exposed to the abrasive local environment increases in parallel. Here is what makes this specific story different from ordinary aviation hazards. The threat is not waiting outside the perimeter fence. It is being pulled directly into the core of the machines that keep the city solvent. Can Dubai multiply its ambitious flight capacity without multiplying its exposure to the abrasive terrain surrounding it? To find the answer, we have to bypass the passenger terminal and follow the dust itself. We must track the precise journey of a mineral particle moving from the hazy local airspace directly into the intense core of a commercial turbofan. The entire process begins right at the intake. As the aircraft pushes down the runway, massive volumes of air are sucked into the massive circular opening. Along with that critical oxygen comes whatever happens to be suspended in the weather system. The first point of physical contact is the large titanium or composite fan blades spinning at the very front. Because these blades rotate at thousands of revolutions per minute, the larger, heavier grains of sand are typically struck and centrifuged outward. They are forcefully flung into the outer bypass duct, exiting the rear of the engine without ever touching the sensitive inner workings. But the finer dust particles, the microscopic silicates that create the permanent haze over the region, behave differently. They are light enough to slip past the fan and be carried straight into the core. Think about the leading edge of an internal compressor blade for a moment. Its curvature is engineered with a level of precision that borders on absolute perfection, designed to slice the air and build pressure. Now imagine hard, jagged mineral particles striking that exact, perfect edge at hundreds of miles per hour. A large rock or a bird might strike the front of an engine and bounce off. But the microscopic particles create an entirely different, far more complex problem, deeper inside the machinery. Does a dust storm really end when the local weather radar shows a clear sky, or only when the engine is finally opened and inspected by a mechanic? Before those suspended silicates ever reach the combustion chamber, they must pass through an environment of rapidly escalating pressure, the compressor. As the air is forcefully squeezed through multiple stages of tightly packed, spinning metal airfoils, the dust particles act as microscopic projectiles. They continuously impact the leading edges and scrape along the smooth surfaces of the blades. This introduces two very different mechanical phenomena. The first is fouling. This occurs when dirt and minerals stick to the surface of the blades. The previously smooth metal becomes coated, rough, and highly inefficient. Fouling is an operational nuisance, but it is manageable. Airlines routinely perform chemical engine washes, spraying specialized detergents and heated water through the core to strip away the accumulated grime. The second phenomenon is erosion, and erosion cannot simply be washed away. As thousands of sharp mineral particles bombard the blades at extremely high velocities, the compressor is effectively being sandblasted from the inside out. Slowly, relentlessly, the precise aerodynamic shape of the blade is physically altered. The metal is worn away. The razor-sharp leading edge becomes noticeably blunted. The smooth surface becomes pitted and rough. When that critical aerodynamic shape changes, the airflow separates. The compressor loses its optimal pressure ratio. The engine begins to run inherently hotter and is forced to consume more aviation fuel just to generate the exact same amount of thrust. This is not a theoretical hazard. A 2025 engineering study subjected a turboshaft engine to 54 hours of continuous sand and dust ingestion. The results were highly specific. The engineers documented a measurable degradation in power, a distinct increase in specific fuel consumption, and rising turbine exhaust temperatures. Physical wear was thoroughly recorded on the compressor components. This does not mean a commercial Dubai airliner loses the exact same percentage of power after flying through a sandstorm. It means that controlled, rigorous testing has proven that prolonged particle ingestion produces measurable mechanical deterioration. How much damage must silently accumulate before a heavy aircraft begins burning significantly more fuel simply to achieve the same takeoff? Compressor wear is a severe economic and operational issue, but the microscopic dust particles that manage to survive the violent journey through the compressor face an even more hostile destination. They are forced directly into the high-pressure turbine. This is the absolute heart of the engine. The temperatures in this section routinely exceed the natural melting point of the specialized alloys used to construct the turbine blades. Inside this extreme inferno, the chemical and physical nature of the desert dust fundamentally changes. When specific silicates and mineral aerosols are exposed to these staggering temperatures, they can soften or turn entirely molten. Instead of bouncing off the metal surfaces, they adhere to them. This molten material strikes the intricate turbine nozzle guide vanes and the rapidly spinning turbine blades, baking into hard, glassy deposits over the precision cast metal. But the most critical vulnerability lies just beneath the surface of those blades. To prevent the metal from melting in the exhaust stream, modern turbine airfoils are manufactured with hundreds of microscopic cooling holes. High-pressure air from the compressor is bled through these tiny channels, flowing out to create a thin, protective film of cold air enveloping the blade. What happens when the air intended to cool those blades is carrying molten mineral deposits? The glassy material begins to collect around these microscopic openings. Over time, the deposits can narrow or partially clog the cooling holes. When that vital airflow is restricted, the protective film breaks down. The internal temperature of the metal blade begins to spike. Operating at a higher temperature severely impacts the long-term structural integrity and lifespan of the component. The engine may continue operating perfectly fine on the flight deck, but continued operation does not mean the internal component is completely unchanged. It is quietly absorbing thermal stress. What happens when the system designed to protect a turbine blade from extreme heat is itself being choked by material pulled from the air outside? A massive, apocalyptic sandstorm rolling over the city makes for incredible television. It creates immediate delays and dominates the headlines. But for the engineers and financial planners tasked with keeping this aviation system solvent, the most dangerous threat is not the singular dramatic event. The most insidious threat is the slow, quiet, daily accumulation of exposure. It is the repeated, unavoidable ingestion of dust during thousands of routine takeoffs and landings, when the sky actually looks relatively clear to the naked eye. Even on a bright sunny day, fine mineral matter remains suspended in the lower atmosphere over the peninsula. Modern aviation researchers have started mapping this hidden reality by combining actual flight trajectories, advanced meteorological tracking, and dense dust concentration models to estimate the total volume of particulate matter an engine swallows during its time attached to the wing. This means the wear happens incrementally, between scheduled maintenance checks. It is the total sum of abrasive material inhaled over 12, 18, or 24 months of continuous service, which is more difficult for a massive aviation hub to financially manage. One massive storm, powerful enough to cancel a day of flights, or years of smaller, invisible exposures that rarely make the evening news. This is the part I find most unsettling about modern infrastructure. A spectacular, sudden failure would be highly visible and immediately addressed, but a gradual degradation can remain totally hidden inside a mechanical system that still appears to the public to be operating normally. The storm is over. The exposure is not erased. Could the greater risk to this system be not a single engine failure, but the relentlessly growing amount of maintenance required to prevent one? If the mechanical damage is truly cumulative, then the real battle against the desert is not fought in the air. It is fought inside the cavernous maintenance hangars. The financial burden of operating in this specific environment must be divided into two distinct realities. The first is the immediate operational cost. When visibility drops due to airborne dust, the airport must implement low visibility procedures. The arrival rate slows down. Flights are placed into holding patterns or diverted to alternate airfields. In a city where the tourism crisis looms the moment luxury hotels sit empty, a delayed passenger is a direct hit to the broader economy. The second reality is the long-term mechanical bill. This involves endless cycles of borescope inspections, where technicians thread specialized cameras deep into the turbine to search for glassy deposits and microscopic erosion. It means pulling aircraft out of revenue service for frequent compressor washes. It requires meticulously tracking performance trends and replacing incredibly expensive, precision-machined turbine components long before they would normally wear out in a milder climate. We do not have public, fleet-level data showing Dubai's total dust-related engine maintenance bill. Without that highly guarded corporate information, no outside observer can honestly calculate the exact financial penalty the desert extracts from the airlines. But the underlying mechanisms requiring these inspections, the rigorous cleaning schedules, and the constant component monitoring are universally established engineering facts. The cost exists, and it requires a massive, complex infrastructure of human labor and spare parts just to keep the friction at bay. How much must Dubai continuously spend simply to prevent ordinary, daily desert exposure from evolving into an extraordinary operational failure? This invisible maintenance burden takes on a completely different dimension when you look at the city's immediate future. Dubai is not satisfied with its current volume. It is actively preparing to eclipse it. The development of the Al Maktoum International Airport project, advancing with an announced budget of roughly 128 billion dirhams, is designed to eventually process up to 260 million passengers every single year. It is a blueprint for an aviation footprint vastly larger than the current operations at Dubai International. Dubai's primary answer to aviation growth is a larger, more capable airport. But a larger airport inherently means that every single environmental challenge must be managed, funded, and repaired at a correspondingly larger scale. More flights equal more intakes breathing the exact same atmospheric dust. Does building the world's largest airport also multiply the mechanical problem Dubai has never been able to completely eliminate? To be analytically fair, aviation engineering is rapidly evolving to meet this exact threat. Airlines utilize highly sophisticated weather forecasting to avoid the densest dust concentrations. Engines are being designed with advanced core architectures, specialized thermal coatings, and smarter airflow pathways. Rigorous preventative maintenance routines catch wear long before it threatens the safety of the aircraft. The industry is highly proactive, but mitigation is not elimination. Every protective measure, every specialized coating, and every new inspection protocol becomes yet another system that must be funded, managed, and expanded. In my view, this is the real engineering question of the decade. It is not whether Dubai has the capital to construct a larger airport. It is whether the system can control the compounding environmental cost of operating it at the promised scale. When analyzing Dubai's infrastructure, the narrative too often swings wildly between unquestioning admiration and sensationalized apocalyptic doom. The engineering reality is much more grounded, and in many ways, much more expensive. Let us be completely precise. There is no public evidence of a systemic wave of dust caused jet engine failures sweeping across Dubai's aviation system. The planes are not falling from the sky. The airlines are flying safely every single day. But there is absolute, undeniable engineering evidence that sand and mineral dust can erode compressor components, form dangerous deposits inside the turbine, interfere with advanced cooling holes, reduce fuel efficiency, and massively increase the required maintenance intervals. Dubai has already proven that human ambition and engineering can successfully operate a colossal aviation hub in the middle of a harsh, unforgiving environment. But scale does not erase the laws of physics. The desert is highly unlikely to bring Dubai's aviation system down in one dramatic, catastrophic event. The more credible, persistent threat is slower. It is a permanent mechanical and financial burden, growing quietly alongside the airport itself. If Dubai eventually doubles or triples its aviation capacity, will advanced engineering keep reducing that hidden burden, or will the desert inevitably collect a larger price from every single aircraft passing through it? Would you trust an aviation system to keep expanding in an environment that is constantly wearing down its most precise machines? Tell us which hidden Dubai infrastructure risk we should investigate next. This documentary examines established engineering mechanisms and publicly available aviation data. It does not claim that Emirates, Dubai airports, or any specific aircraft fleet is currently experiencing a systemic engine failure crisis.